this morning for you guys. So less technical, more high-level remediation discussion. But specifically, I wanted to talk about sustainable remediation and applying a life cycle approach to your designs and really in that selection of remediation process. So a little bit about me. My name's Matt. I'm an environmental engineer. That's sort of where I'm coming from. It's from an environmental engineering perspective. I work at Gradient. We're based in Boston. Beautiful Boston skyline there for you. We work on sort of environmental science and risk assessment. But the focus of this presentation and sort of coming to an electric utilities conference is we're starting to work. We work for a lot of utilities, and then also on a lot of CCR projects. Specific to this work, I work on a lot of corrective action analyses, FEIN transport chemistry projects, big litigation projects. But Gradient as a whole, we work across the country. We're headquartered in Boston, but we have people across the country working on these service areas and more. All right. So just to sort of intro you to what I'll be talking about, just sort of a background on sort of the trend we're seeing in sustainability and the growth and prevalence of life cycle assessments and approaches like these. Then I'm going to kind of intro you guys into life cycle assessments, that process, the current ISO standard process. And then to sort of illustrate the process of applying lifecycle assessments to a remediation project, we've actually created a hypothetical site where we apply these principles to the site, and then we'll sort of discuss the outcomes of applying this process. So this is where we're coming from, right? In the United States, we've been a little slower, but even starting back in the late 2000s, there's been executive orders sort of putting sustainability at the forefront of federal processes. More recently, there's been a federal sustainability plan, which looked to set limits and targets for net zero emissions. There's also new proposed SEC disclosure rules. And then in the EU, our counterparts that tend to be a little more aggressive or progressive on sustainability issues. There's a slew of regulations and acts focused on circularity, life cycle assessments, and having a better understanding of carbon impacts throughout processes and products. Green and sustainability remediation efforts have been put forth across many U.S. agencies and state agencies. Green and sustainability remediation really is just the focus of not so much the groundwater protection standards and achieving the primary standards, but also thinking about the secondary standards when creating an environmental design. So considering environmental effects, local community, things along these nature. So I've listed just a few examples, but in most states, there's some sort of activity or initiatives put forth by environmental departments. All right, so just discussing life cycle assessments. As I said before, they're kind of be a key process to understanding carbon outputs and carbon hotspots in processes. As I mentioned before, the standard on this from ISO is the 14,000 series, which creates a standard methodology that I assume will only improve as life cycle assessments will become more popular. So it's a standardized approach for creating a life cycle assessment. And life cycle assessments themselves are really just a way to receive and evaluate environmental impacts for a variety of products and processes, and it really takes a holistic approach, sort of understanding from sort of like the extraction phase to maybe the disposal phase of your product or process. And so the area I'd like to apply lifecycle assessments to is the area of remediation. And the reason why I think this is a good fit and why we've used this before at Gradient is the unique ability to take this standardized approach of lifecycle assessment and compare various alternatives and receive output of environmental impacts across different alternatives. And then also you gain the ability to sort of understand more about your process and the selected remedial design you may go forward with. So in addition to this, you can meet internal standards, which may be important for your business, for example, ESG standards. When designing a remedial action, you may encounter community acceptance. Is really important. So bringing a project where you've performed and have environmental impacts completed will be very impressive for any sort of public meetings you may have to present your project to. In addition, there's no federal regulation, obviously, dictating lifecycle assessments be performed. However, agencies like to see that you have put forth thought towards protecting the environment in your design. And then, of course, the last area, which I think is important as an engineer, is sort of when we catalog and understand the data and inputs we're putting in, we can sort of optimize sort of areas where we're using too much of a material or energy can be better used. And this is some of the power of lifecycle assessment. So stepping through what is sort of recommended by the ISO and the ISO series for lifecycle assessment, the first step is to sort of set your goals and to scope a lifecycle assessment, which seems kind of obvious as a first step. However, the limitations of a lifecycle assessment is really your contextualizing results in this scoping phase. So it's really important that you have a good idea of the type of phases you'd like to consider, some of the limitations of the research you're going to be doing, and some of the assumptions that you took to get your results. Then moving forward, the next step is the inventory analysis. So this is taking raw material and energy you'll be using, and then aligning that data with functional units that are available from a LCA database. So one example of a database could be EcoInvent. These are databases that you can input sort of the quantity or the energy into, and then you can input this value into a database in a software. The next step would be sort of choosing an impact assessment. So you're going to target different environmental impacts that may be important to stakeholders. And there's really a good amount of impact categories that can be automatically calculated for you as soon as you align data into a database. And so this includes ozone depletion, acidification, important to most people, global warming. But you can also understand ecotox values and carcinogenic impacts. And sort of the last step, and a step that happens throughout the process, is interpreting these results, contextualizing these results, and adjusting the scope or the data you want to use throughout this process. Okay, so to illustrate this example and how it can be applied to remediation specifically, my colleagues and I have created a hypothetical CCR site, a site that's been impacted by groundwater with typical CCR contaminants such as boron, arsenic. And we've chosen 3 alternatives to treat this groundwater plume. The first being monitored natural attenuation, a process of installing monitoring wells and naturally having groundwater attain groundwater protection standards. The second alternative we considered was installing and reinstalling a permeable reactive zone. And the third alternative was a pump and treat system whereby extraction wells would be installed and a treatment system would be installed on site. Really, the goal of sort of this analysis will be to understand two things, right? To compare across these three alternatives, which will perform best under a life cycle assessment, and which environmental impacts will be the least, and then ultimately, how can we improve the sustainability within these alternatives? So, as I said before, scoping a life cycle assessment is very important. So I have here the system boundary drawn that we'll be considering, and I'll be putting flowcharts of each of the alternatives onto the screen. But really, we considered four big phases of environmental impact potential. So the first being the equipment of supply, or the materials we'll be using, the transportation from the product source to the site, and then the impacts related to any site constructions that's necessary. And then the fourth will be the operation and maintenance and the continuance of any action that we'll consider until groundwater protection standards are met. So the flows into the system are going to be the energy and raw materials and the data we'll need for that, and then the outflows will be any emissions to the air, water, or soil. Importantly, we didn't consider solid waste in one of the life cycle phases, and this was just because of some of the incompatibility with the LCA databases available. All right, so let's see. For the first alternative, the monitored natural attenuation alternative, we considered the well construction material production, environmental impacts, the transportation to the site, and then, of course, the well drilling, well installation, and then sampling installations. So monitored natural attenuation will obviously have the least impact on our hypothetical CCR site. The next flowchart to sort of illustrate the components that are going to be going into the environmental impacts for this alternative. We considered a reactive zone with the treatment material being zero-valent iron. And then for the site construction, it's going to be limited to the construction of the reactive barrier, and then the trenching, and then obviously in some cases, a reactive barrier may be removed and reinstalled, and that was the case for the given parameters we were using. So we consider in the operation and maintenance phase a reinstall of the reactive barrier. And then also we have monitoring wells to sort of engage with the knowledge of what's going on in our system. Okay, and then the final alternative was the pump and treat system. So the equipment required is going to be the treatment house, the treatment materials. We chose granular activated carbon and an ion exchange treatment train. We're going to need energy supply for the extraction wells and pumping related to the treatment house. The site construction is a little more complicated for this alternative. There's trenching, treatment house installation, extraction wells to be drilled. And then the operation and maintenance was limited to extraction well maintenance, ion exchange, regeneration, and media replacement changeouts. Okay, so after compiling sort of the data we needed for this hypothetical site, we input we try to align these values with an EcoInvent database, and then we used an LCA software to choose a life cycle assessment analysis to sort of get the following results. So I've limited the environmental impact results to 3 categories for this discussion, but just note that you can you can determine a wide variety of environmental impacts. But I've chosen global warming, fossil fuel depletion, and smog just kind of as important environmental impact assessments that may be important for state regulations. So the first goal of performing this was to sort of understand the relative impacts by phase and sort of understand key drivers for each alternative. So I have the relative impacts by phase here. And so to understand what the biggest drivers were for each, we found that for global warming, zero valent iron was actually the production and the extraction to market for zero valent iron was actually the predominant impact. So if you were to redesign or if you were to run this life cycle assessment, you could reevaluate your design to use less zero valent iron, or you could consider a different treatment media for your permeable reactive zone. So the next outcomes of sort of running this result was to understand the pump and treat major drivers, and really half of the global warming impacts were from the pump operation. And so remember, we used energy from a grid, and so we were able to sort of understand that most of the impacts are coming from that pump operation. So some options to fix this would be perhaps install a renewable energy source to replace the grid, or consider running pumps less frequently or on a lower regime. The other half of this contributor was also the production of material needed for the site. All right, and then looking cumulatively across the different alternatives, the permeable reactive zone performed the worst and had the most impacts, which makes sense. There'd be a lot of material required for multiple trenches and changeouts. And then, as expected, the monitored natural attenuation alternative had the least environmental impacts. Okay, so to contextualize results, which again is a very important step when you're performing a life cycle assessment, and to sort of point out error to sort of understand results. We kind of created 3 categories of possible qualitative error. So the first was the ability to match an item that we needed for remediation to an eco-invent database. So these databases are pretty typically used for products. So typically you're building something physical, and you're not really applying this process to remediation. So that was one problem we had a lot, and the way we sort of went around this was we found similar materials. So this could be one source of error. The second source of error we ran into a lot was an inventory region match. So we wanted to consider a CCR source somewhere in the United States. However, a lot of the values that were calculated in a database were from either Europe or Australia or global values, and this can have a big impact based on where a product is made or where energy is being produced. And so the third possible source of error was some of the uncertainty that we used to actually input into the database. And this uncertainty can be kind of tied to the fact that we used a hypothetical site, and some of the information was lacking in how far a subcontractor would travel to a site. So a lot of these values were assumed or were used based on previous project information. So some of the takeaways from this, we can apply life cycle assessments, and really state and federal green and sustainable remediation programs are sort of looking at high-level design that considers these values, and a life cycle approach aligns to initiatives that have already been put out by programs. In addition, we know that sustainability trends are increasing, and remedial designs that are inclusive of considerations of not just performance, but also environmental effects and also health effects and risk effects will only increase over time. And I just wanted to put this out there as well. Obviously, this process can be applied not just to remediation, but it's also a powerful tool overall to evaluate environmental impacts and your various sustainability goals. So with that, I'll close it there. This is my contact information here, and then these are my contributors at Gradient who helped with the project. And I'm also open to questions. Thank you.
I have a question, but I don't know how to pose it.
Yeah, no, go ahead.
In relation to CCR, well, let's just ask this first. Everybody wants to get their SGs better.
Yeah.
You know, whatever. Okay. So, and I'm trying not to be condescending when I talk about this.
No, it's okay.
Have y'all dealt with EPA directly and trying to show how one of these could help with a particular program?
Yeah, no, so not with EPA directly. We have.
I can give you an example. We got a surface impoundment, very large. Regulatory authorities think we ought to clean close it. We're talking tens of millions of miles of trucking to clean close it.
Yeah.
So where does being green fit in?
Sure, yeah.
That versus closing it, and we feel like we've got a good.
Yeah, I think a good.
We don't really have that.
I think a good fit for this is when you're in the process of selecting the type of removal. If you have a couple options for removal, you could, and this is sort of like presenting sort of a report to EPA. You could list, or you could put together different options, and then sort of apply. Maybe not an extensive life cycle assessment, but you could have definitive results about what are the environmental impacts. And for example, if you wanted to argue to EPA, or you have an order to remove material, you could also use something like this as a mechanism to explain, okay, well, this material is in the ground right now, but if we remove it, you're going to release this amount of carbon dioxide from the trucking to move it from landfill, or So
that's my point. It makes absolutely no sense.
Exactly.
So is a tool like this, will they pay attention to it? This is what I'm curious about. If y'all ever.
I mean, some of the experience we've had was with local communities, and they wanted to sort of have an understanding of, what are the impacts of a impoundment near me versus what would be the impacts of construction and the removal by my community be. And so a client comes to us and they say, can you sort of articulate this understanding? And we would say, okay, well, the trucking is going to cause this amount of carbon dioxide, and you can also do other impacts like ozone or carcinogenic effects, and so you can kind of create a quantitative argument as much as just saying there's going to be trucking by your house, it's going to be disruptive. But yeah, good question.
Hope that came out.
Yeah, no, that's a good question. That's fair.
I'll just follow up to that.
Yeah.
So how many of those studies have you performed working with?
Yeah, no, so this is relatively new for our service area, so we're trying to sort of break into sustainability. We have a few power clients who are interested in life cycle assessment, or environmental footprint is kind of like a less intensive analysis, and we've done footprint analyses before, as well as sort of risk assessment heavy projects with sort of eco-tox side and exposure. So yeah, we're definitely breaking into it, and an extensive life cycle assessment. We haven't performed that much for clients, but in the past we've done sort of footprint analyses and precursors to something as intensive as a life cycle assessment.
We have time for one more question.
All right, so as I mentioned before, I got business cards up there, and I appreciate the great questions and for coming out so early. Sweet.